my name is Ginny Canestraight, and today we're going to be talking about chirality. The word chiral comes from this Greek word, which means hand. Why? Because hands are the most obvious example of chirality in nature. If something is chiral, it means that you take its mirror image, and no matter how you twist them around, you can't ever superimpose them on each other. So if you take your hand and the mirror image of your hand, you can never exactly line them up. They're always going to be opposite, right? It's the same thing in chemistry. So if you take a carbon that has 4 things attached to it and you mirror it, then you get a similar looking molecule. However, if you try to rotate it so that they line up, you'll see all 3 balls match except one. On one molecule, the blue is coming towards you, and the other is going away. These molecules are not equivalent. But the golden question is, why should I care? Many things in nature exhibit chirality. We already talked about the example of your hands, but another good one is shells that you might pick up on a beach. They curl one direction because of the components that make them are chiral. Your DNA is only ever going to twist clockwise, never counterclockwise. Every sugar that your body uses is called a D sugar, and all the amino acids are L. There's a chemical called limonene, and one version of limonene is what makes an orange smell like an orange. But the other mirror image of it is what makes a pine tree smell like a pine tree. The same goes for a chemical called carvone. Carvone makes your spearmint gum smell like spearmint, but the other version of it is found in caraway seeds. It's important to note that if you have a molecule that is achiral and the 2 mirror images of a molecule, they're going to react in the same way no matter what. But if you have something that's chiral and you have something chiral reacting with it, that's when things start to get weird. Imagine taking a whisk. The whisk works equally well in your right hand as it does in your left hand. However, if you grab a pair of scissors, the scissors feel good in your right hand, but if you pass them to your left, oh, they feel weird. They're not shaped for your left hand. They don't react. Our body reacts in different ways with different versions of a molecule, and that's why you know that one version of limonene is orange and the other one is pine, and it isn't all mixed together. These mirror images react very differently, so they're very important to pay attention to, especially in the drug industry. There are many drugs that are marketed as mixtures of both mirror images of a drug, and one mirror image of them either doesn't do anything or it has a positive effect. However, there have been cases where one mirror image of a drug will have a positive and the other will have a negative effect. This was the case in the thalidomide tragedy, where a drug was supposed to help women with morning sickness, but the mirror image of it actually gave their babies birth defects. So obviously very important to pay attention to chirality in drugs. But the biggest question is, where does chirality even come from? Scientists used to think of it as a chicken or the egg type problem, which came first, because we thought that you needed to have a chiral catalyst or environment to create a chiral molecule. Now we know that that's not the case, and you can create chirality from a set of achiral starting reagents. However, we're not exactly sure how this happened or even when it happened. All we know is that at one point in history, nature decided that sugars were D and amino acids were L. Scientists liken it to a coin toss. If it had happened the other direction, our world would probably look exactly the same, except all living things would just be mirrored from what they were. So, in essence, our world is only one mirror image, and if you look in the mirror, the thing on the other side doesn't always react and behave the same way that you would. And that's chirality.